In section 3.8, we're looking at implicit differentiation. Knowing how to use implicit differentiation allows us to take the derivative of an entire another set of expressions. We're used to looking at expressions like y equal 2x plus 3. This is called an explicit form. We call it explicit because I have solved for y explicitly in terms of x, meaning I have y's on one side, just a y on one side, and all my x terms are on the other side. Now taking a derivative here is pretty easy. The derivative of y with respect to x then is just the derivative of 2x, which is 2, the derivative of a constant, which is 0. So this is the easiest case to work with when we're talking about taking derivatives. What if we move the 2x across on this one? What if we had y minus 2x equals 3? Actually, let's move the 3 across as well. Y minus 2x minus 3 equals 0. This is called implicit. This is called an implicit expression. It's called implicit because my x's and y's are mixed together. I don't have a y equal or an x equal in terms of the other variables. So here I have a mixture of my variables x and y. So in this one, I would like to go ahead and find the derivative again of y with respect to x. Well, when we look at the derivative of y with respect to x here, it's not as obvious as it would have been up in the explicit form. Solving for dy dx here is not going to be as clear. So the first thing I would do is I would take the derivative of y with respect to x. That component is going to look like dy dx. I took the derivative of y with respect to x. The derivative of minus 2x is going to be a minus 2. The derivative of a minus 3 is just 0, plus or minus 0, it doesn't matter. And of course, the derivative of 0 is 0. So solving here, I get dy dx, add the 2 across, equals 2. So these answers match, but we can see that in its explicit form, it's a lot easier to solve for. Now, we could have just gone through and solved. This one worked pretty straightforward, but sometimes an equation cannot be solved for explicitly. And these are the toughies. So again, I could have come up here and solved for y and gotten y equal 2x plus 3, solved for explicitly, and then taken my derivative. But not all equations can be solved for explicitly. Let's go ahead and look at an example where this is the case. In this particular example, let's go ahead and look at the equation x squared plus 2xy plus y cubed equals 7. And I would like to find dy dx or y prime, however you want to notate that. Well, if we look at this expression, I can see pretty clearly that I cannot get x's alone and get x equals stuff only in terms of y, and I cannot get y alone to get y equals stuff only in terms of x. So I'm going to have to use implicit differentiation here. Now when we use implicit differentiation, we need to remember that I am taking the derivative of the function y with respect to x. The variable of interest here is x. So whenever I take the derivative with respect to a different variable like y, I need to tack on that dy dx or dz dx or dx dt depending on what my variables are. So let's go ahead and start looking at this from implicit differentiation perspective. Again, we're looking at x squared plus 2xy plus y cubed equals 7. Now some parts of this will be easier than others. For instance, this will be the derivative of a constant, which is 0. This will just be a good old nice derivative. X squared is 2x. Here I'm going to have to use a product rule because I have a function times a function. And then this one is going to be pretty easy, but I need to remember that implicit component here. So what's the derivative of x squared? That's just good old 2x. Now the derivative of this next piece, like I said, is going to be the product rule. Now the product rule says I have the first function times the derivative of the second function. Well, the derivative of y with respect to x is just dy dx, plus the second function times the derivative of the first function. Okay, the derivative of y cubed is 3y squared But I just took the derivative with y with respect to another variable. So if you want to look at it like this, I'm actually using the chain rule. So the derivative of the outside is 3, bring the 3 down, decrease the exponent by 1, and the derivative of y with respect to x is the derivative of the inside, that's my dy dx. The derivative of 7 is 0. So trying to map this out a little bit, this whole piece right here is my product rule. This piece right here was implicit differentiation, and the derivative of 7 is 0. Now we haven't actually taken the full derivative yet. 2x I'm done with. 2x dy dx. Now some people use y prime here. It doesn't matter to me which one you use as long as you realize it's not a y to the first. Plus y, the derivative of 2x is 2, and the derivative of my y cubed was 3y squared dy dx. I took the derivative with respect to a variable other than x, so I need to make sure I apply that chain rule and put my dy dx or tack on your dy dx there. And again, it's just the chain rule piece. Now it's algebra. I need to get dy dx is on one side, everything else on the other side. So let's go ahead and put 2x plus 3y squared dy dx. And that comes from right here, 2x, 3y squared. If you factor out a dy dx, I'm left with 2x plus 3y squared. And we're going to move everything else across. So I'm going to move the 2x across. That will give me a negative 2x when I subtract it across. I'm going to subtract over 2y. Because it's a positive on the left, it becomes a negative on the right. And it looks like I have my 1, 2, 3, 4 terms, so I'm taken care of. I have a 0 on the right. And then to go through and solve for dy dx, I actually divide through by 2x plus 3y squared. Whatever you do to one side, you have to do to the other. So therefore, I get dy dx is equal to minus 2x minus 2y over 2x plus 3y squared. This has the same meaning as always. This is the slope of the tangent line at any point. Now usually what ends up happening is I plug in an x value. Now I'd have to not only know my x value, but I'd have to know y value as well. And this could be simplified a little bit, but this is good for implicit differentiation. So again, if you would want to evaluate, you need both an x and a y value. Okay, let's go ahead and look at another example. In this next example, we don't have an equation. If you recall from up here, this was an actual equation. I had an equal sign involved. So see, I had an equal sign. In my next one, we don't have an equal sign. It's just an expression. And our rule is to differentiate x squared plus y squared to the 3 halves with respect to x. Because we have two variables, so I could take the derivative with respect to y or x, and so the directions are telling me the variable that I'm taking the derivative with respect to. Now a lot of times we write the words with respect to so often we abbreviate it WRT, so with respect to x. Now this one I don't have an equal sign, so I'm not going to be able to solve for dy dx. I'm not going to be able to get dy dx equals. Next thing I note on this one, this is going to be a really nice chain rule. I have a function to a power, so I go ahead and take the derivative of the outside times the derivative of the inside. So when I'm taking my derivative, I bring the 3 halves down. I decrease the exponent by 1. My old power was 3 halves. 3 halves minus 1 is a 1 half. Now I take it times the derivative within. So let's go ahead and look at this. This is outside prime, derivative of the outside. Now this piece is going to be inside prime, or the derivative of the inside. Now to take the derivative of x squared, I just get 2x. The derivative of y squared is going to be another chain rule. It's going to be 2y, and then the derivative within is dy dx. Because I just took the derivative with respect to a variable other than x. Now if you want to think of the derivative of x squared as 2x dx divided by dx, which it actually is, I'm actually using the chain rule with that one as well, except for dx divided by dx is 1, dy divided by dx is not equal to 1 here. So there's no equal sign here. There's really nothing else I can do here. I did take the derivative, so you cannot solve for dy dx here. this is actually my solution. So there's no equal sign. So you can't solve for dy dx, but this is the derivative of that expression. Let's go ahead and look at another example where we're using trig functions. Of course, you have to know your basic trig derivatives. You're going to have to use your product rule, chain rule, quotient rule. All your rules are going to be mixed in here. So for this example, I would like to find dy dx of tangent x squared y, and oops, right there, there's my product. Okay, here's my implicit is equal to x plus y. On the right hand side I don't have a product, but I do have implicit that I'm going to have to worry about everywhere that you see a y. Now to start with our derivative here, first of all, I do have an equal sign, so I can solve for dy dx in the end. That's the first thing to keep in mind. Okay, so starting, the derivative of tangent is going to be the secant squared argument, or u, secant squared u, times the derivative with respect to x of the argument. This is going to be a product rule, and of course the chain rule will come into play when I take the derivative of y. I've not taken the derivative of this expression yet. Now on the right hand side, the derivative of x is 1, the derivative of y is 1 dy dx. Because I took the derivative with respect to a variable other than x, I need to make sure I use that chain rule with my implicit differentiation. So secant squared x squared y, the argument never changes when I take the derivative of a trig function. Now I'm going to have a product rule. So my product rule is going to be the first function, which is x squared, times the derivative of y with respect to x, which is 1 dy dx. Okay, plus the second function times the derivative of the first function. And then on the right hand side I have 1 plus dy dx. So I've done all the work that's the calculus part of this. Now I need to do the work that's the algebra portion. I need to get all my dy dx's on one side, everything else on the other side, and hopefully be able to solve. So it looks like to me I can take the secant squared and distribute it through, and then I can keep my dy dx's here, move this piece over, this dy dx to the left, keep the 1 on the right, and solve. So let's go ahead and see how that looks. X squared, secant squared x squared y, and then this is my dy dx. So again, this is just secant squared x squared y distributed to this first term, okay, plus 2xy secant squared x squared y. That is just this secant squared x squared y distributed through to the second. I'm going to go ahead and subtract this dy dx across, and I get equals 1 here. So this dy dx I just moved across. Next thing I'll do is I'll gather my like terms. So I'm going to gather my dy dx's, and then I'm going to take this piece and move it across. So in gathering my dy dx's, it looks like I have x squared secant squared x squared y minus 1 dy dx. Because if you factor a dy dx away from a negative dy dx, you're left with a minus 1. Okay, equals 1, I'm going to subtract this across, 2xy secant squared x squared y. And if you're not sure on the algebra, go through and show these step by step. The last thing we're going to do is divide through by the coefficient in front of dy dx. Whatever you do to one side, you have to do to the other. And I get dy dx is equal to everything that's right here on the right. So I have 1 minus 2xy secant squared x squared y all over x squared secant squared x squared y. And that's my derivative. Now again, what's the meaning of this? This is the slope of the tangent line at any point along the graph. If you wanted to know the slope at a specific point, I would not only need an x value, I would need a y value to do this. So let's go to an example and look at where we find the slope of a tangent line at a specific point, where we actually get to evaluate one of these functions. This one's nice because they actually give us an x and a y value on it. So what we want to do is we want to find the slope of the tangent line at this point, at this x value. This x value is 2 minus pi over 4. The y value is pi over 4. And I want to find the slope of the tangent line at that point to this function, sine squared 3y equal x plus y. Now this one I could actually solve for x explicitly because I could x equals stuff in terms of y, but I don't want dx dy, I want dy dx, so I have to use implicit differentiation here. So the first thing I want to do is to find the slope of the tangent line. So the slope of the tangent line, we abbreviate with an m, and that's going to be dy dx evaluated at 2 minus pi all over 4 pi over 4 for my y value. Get a little extra parenthesis there. So let's go ahead and get started finding this value of dy dx. First thing I note here is I'm going to have a chain rule. It kind of looks like I have a product rule here, but really it's just, I could use a product rule, but it's easier just to take the derivative of 3y, but I'm going to have to remember it's implicit. And on the right hand side I'll also have some implicit differentiation occurring. So the first thing I'd like to do is go ahead and rewrite this. This is the sine of 3y quantity squared equals x plus y. Then I can see my chain rule pretty fast. I bring the 2 down, decrease the exponent by 1. Remember, the arguments never change when we take the derivative of a trig function. So I bring the 2 down, I decrease the exponent by 1. That's the derivative of the outside. Now I need to take the derivative of the inside. The derivative of sine of an argument is the cosine of the argument times the derivative of the argument. So here's my chain. It's another chain rule. The derivative of 3y is 3. The derivative of my y right here, I need to remember I'm taking the derivative of y with respect to x, so I need to tack on that dy dx. So let's go ahead and look at this one more time. You bring the 2 down, decrease the exponent by 1. That's the derivative of the outside. Now this piece right here is the derivative of the inside, but within the inside I have another outside and inside. So again, you bring the 2 down, decrease the exponent by 1. That's the derivative of the outside. The derivative of the sine of u is cosine u prime. In this case, the derivative of 3y is 3 dy dx because I took the derivative with respect to a variable other than x. That's the implicit portion here. On the right hand side, the derivative of x is 1. The derivative of y is 1 dy dx. Now if I wanted to at this point, I could start plugging in x's and y's from up here. And actually, as it turns out, it looks like we're only interested in this y value because I don't see any x's left here. So if I wanted to, I could start plugging y's in right away, which is absolutely fine if you choose that. I'm going to simplify a little bit. So in simplifying, it looks like we end up with 2 times 3 is 6, sine of 3y, cosine of 3y, minus 1 dy dx equals 1. Okay, now where'd the minus 1 come from? I subtracted this 1 dy dx over to the left, and then I factored a dy dx away. Now, when we're trying to solve for dy dx here then, I get dy dx is equal to 1 divided by everything this coefficient right here, because whatever you do to one side you have to do to the other. Sine of 3y, cosine of 3y minus 1. So this is the slope of the tangent line at any point along the graph. Now what I need to do is I need to evaluate it at our point. Well, the point we're interested in was 2 minus pi all over 4 pi over 4. Well, there's no x's in this, so that's going to be easy to evaluate. So again, I'm looking at slope here, which is dy dx evaluated at this point. And it actually turns out that I'm just using the pi over 4. So I'm going to have 1 over 6 sine. When I plug in when I plug in pi over 4, I get 3 pi over 4 cosine 3 pi over 4 minus 1. I'm going to simplify. I get the slope is equal to, so we're running out of room at the bottom. Slope is equal to Okay, the sine of 3 pi over 4. 3 pi over 4 is in the second quadrant. Second quadrant has a positive sign. It's a multiple of pi over 4, so the sine of 3 pi over 4 is square root of 2 over 2. The cosine of 3 pi over 4, 3 pi over 4 is in the second quadrant where the cosine is a negative. It's a multiple of pi over 4. So I have square root of 2 over 2 for the value. For the magnitude, the direction will be a negative, and this is minus 1. Simplifying, looks like we end up with root 2 times root 2 is 2. 2/4 is the same as 1/2, but this is going to be a negative. So again, this is negative 1/2 minus 1. 6 times a negative 1/2 is a negative 3, minus 1 is a negative 4. So I get negative 1/4 for my slope here. So let's go ahead and write the equation of my line now. The general form of the equation that we always start with is y minus y1 equals m times the quantity x minus x1. Well, y1 was pi over 4. That was given to us as an ordered pair from right here. This is given to us as an ordered pair. Is equal to m. M in this case was a negative 1/4. X minus, now this one's going to be a little bit strange. If we look back up at our x value, it's 2 minus pi all over 4. So again, usually we don't have a binomial when we're working with those, but in this particular case we do. Okay, this needs simplified quite a bit. It's not going to turn out real nice, but it will be okay. So you have y minus pi over 4 is equal to negative 1/4 x plus a negative times a negative is a positive 1/4 times 2 minus pi quantity all over 4. And then what we do is we'd add the pi over 4 across. So I have negative 1/4 x plus 2 minus pi over 16 plus pi over 4. Make that look like a plus instead of a t. And we could find a common denominator here by multiplying top and bottom by 4. And I'm not going to worry about a common denominator with this point because it's a separate slope. I'm not going to want to combine them anyway. So I have y equals negative 1/4 x plus, this is going to be 2 minus pi plus 4 pi is 2 plus 3 pi over 16. So negative 1/4 is my slope. This is my y-intercept, 2 plus 3 pi over 16. So that's the slope of my tangent line. Let's go ahead and look at another one of that type. Let's not have this one involving trig. That will certainly simplify it a little bit. Let's go ahead and find the equation of the tangent line. At the point 1, 1 of the equation x to the 1/2 plus y to the 1/2 equals 2xy. Kind of snuck off the screen. So again, the first thing we need the slope. So let's go ahead and find the slope. The slope is the derivative. Well, the derivative of x to the 1/2 is 1/2 x to the negative 1/2. The derivative of y to the 1/2 is 1/2 y to the negative 1/2, but I need to remember to use that chain rule. The derivative of y with respect to x, I need to make sure is multiplied by, that's the derivative of the inside. And this is equal to 2xy, which is going to be a product rule. So I have the first, which is 2x. The derivative of y is 1 dy dx, because I took the derivative with respect to a variable other than x, plus the second times the derivative of 2x, which is just going to be 2. Well, we know the rules. We know how this is going to work. I want to solve for dy dx, but let's do this one just a little bit differently. On this one, let's substitute in my ordered pair right away. So I want to substitute 1, 1 right away instead of solving for dy dx first. On the last one we solved for dy dx first. Let's go ahead and just substitute in for this. So everywhere there's an x, I'd plug in a 1. Everywhere there's a y, I would plug in a 1 as well. Now I don't ignore this dy dx, that's still out there. It's just going to be a lot easier to solve for in this case. So again, anywhere that I have an x, I plug in a 1. Don't ignore the dy dx. And anywhere again I have a y, I plug in a 1 as well. Now this should be a lot easier to solve for dy dx. Well, 1 to the negative 1/2 is just going to be 1. 1 times 1/2 is 1/2. I'm going to get 1/2 dy dx here. And then on the right hand side, I'm going to get 2 dy dx plus 2. Now looking at this is a lot easier to solve for here, dy dx, than it was up here. That was kind of ugly. So let's go ahead and solve for dy dx then. I'm going to have 1/2 dy dx minus 2 dy dx, because I'm going to subtract that across, solving for this algebraically. And on the right hand side I have my 2, and then I subtract over my 1/2. Well, 1/2 dy dx minus 2 dy dx is the same as 1/2 minus 4/2. It's just going to be a negative 3/2 dy dx. And here I'm going to have 4/2 minus 1/2, which is going to be 4/2 minus 1/2 is 3/2. And then however you want to look at this, whether you look at this as multiplying both sides or dividing both sides, we get dy dx equals, looks like -1. That's my slope. Okay, well, to write the equation of my line then, I need my point slope form. And remember, my slope is -1 and my ordered pair is 1, 1. So I get y minus 1 is equal to a -1 times x minus 1, and then we solve for y. The equation of my tangent line is -x plus 2. Okay, that's the equation of the tangent line to the graph of x to the 1/2 plus y to the 1/2, I believe. Yep, y to the 1/2 at the point 1, 1. Okay, let's go ahead and look at one last example. In this one we're going to be looking at higher order derivatives. So we're going to be taking multiple derivatives of an implicit expression. So we want to go ahead and find y prime and y double prime of y cubed minus 3/2 x squared equals 1. Well, let's go ahead and start with y prime. Now this one, instead of using my dy dx notation, I'm going to use a y prime notation, and I don't care which one you use as long as I can follow along and read what you're up to. So for this first part, the derivative of y cubed is 3y squared, y prime, or dy dx if you prefer that notation. And I should make that clear, that's not a y to the first, y prime. Okay, now this next piece is going to be pretty easy. I drag the -3/2 along, I bring my 2 down, the derivative of x squared is 2x, and the derivative of 1 is 0. Okay, let's go ahead and rewrite this. I have 3y squared, y prime, the 2's cancel here, minus 3x equals 0. Solving for y prime, I get y prime equals, add the 3x across, divide through by 3y squared. So I get y prime equals 3x over 3y squared, which of course we can simplify into x over y squared. So here's my first derivative. Now my second derivative, I'm going to have to use the quotient rule on my first derivative. So I'll start with the bottom function times the derivative of the top. The derivative of x is 1, minus the top function times the derivative of the bottom function, which is the derivative of y squared, which will be 2y. Now remember, I just took the derivative with respect to a variable other than x, so I need to make sure I take the derivative of that inside piece to get y prime, or dy dx. And this will be all over the bottom squared, y squared quantity squared. Now in simplifying this, I'm actually going to use my first derivative to simplify. So let's rewrite. Y squared minus 2xy. But what was y prime? Well, y prime was x over y squared, so let's go ahead and plug that in. And this is all over y to the 4th. Of course, we'd never leave it like that. We'd want to simplify. So we have y squared minus 2x squared over y. This y cancels, leaving one y down here, all over y to the 4th. Finding a common denominator, I'd multiply top and bottom by y. and I get y double prime is equal to y cubed minus 2x squared. Now what happens to this y that's common is it goes down into the denominator, so this is all over y to the fifth. So there's my second derivative. So if we're looking at higher order derivatives, remember, if you end up with a y prime, you know what y prime is and you need to substitute for that. These problems can get a little long, but the key feature to remember here is I'm actually applying the chain rule with respect to a variable other than x. So whenever you take the derivative of y, when x is our variable of interest, you need to tack on a y prime or a dy dx. Now this works for other variables too, like t's and z's and r's and s's, but remember you have to look to see the variable of interest, because when it's solved for implicitly you could have more than one variable of interest. Thank you.